I also need to keep this thing on, that is the syllabus. And chemical properties, oxidation state, okay. We only did a reaction towards oxygen, no? And we only wrote about oxides, I guess. Right, oxides. Now we can write reactivity towards water. Okay, just a second. So let me write the order of acidic character of oxide. Okay, order of acidic character. So in the dioxides, you will have CO2 will be most acidic, followed by SiO2, followed by GeO2. Okay, and the rest of them are amphoteric, and then and then the rest of them are amphoteric. They are not acidic. So this is the acidic character. So the most acidic is carbon dioxide. Most acidic is carbon dioxide. Second point is regarding the reactivity towards water. Reactivity towards water. So what happens if you put coal in water? What will happen if you put coal in water? Anything happens? Tell me. What will happen if you pour sand into water? Nothing happens. Even if you heat it, nothing will happen if you pour sand into water, right? So carbon, silicon, germanium, these are not affected by water. Carbon, silicon,
Sir,
and
could you
germanium.
scroll up?
You want to write it? Okay. Silicon and germanium don't react with H2O. Okay, they don't react with H2O. Similarly, then you will write about the Sn, that is 10. So 10 will react with H2O with some heat, and then you will get SnO2 plus H2 plus H2 gas. Then carbon, silicon, germanium, and at last we have tin and then lead. Right, Pb. Pb does not react with H2O as it forms a protective layer of oxide. Write this down. Let me know if you're done. Then we'll write the reactivity towards halogen. The reactivity towards halogen. Okay, done, guys. Khalid, Salman, Imran, Hiba.
Yes, sir.
Done. Okay. Right, next reactivity towards halogen. Reactivity towards halogen. First of all, except carbon, and we can first of all write all the, first write like this, all the group 14 element can form, okay, not halogen, can form halides of formula EX2 and EX3. EX3, EX4, because it has the oxidation state that the group 14 elements they show is +2 and +4. They show the oxidation states of +2 and +4, and hence they can form element E means any group 14 element and two halogens attached to it. Similarly, EX4, where X is any of the halogen. Right, next point. So when you have EX2 and EX3, that means if I talk about the stability of dihalides, okay, stability of dihalides. So if I want to talk about the stability of dihalides, then as we go lower the group, the stability of dihalides, it will increase. The stability of dihalides, it will increase. So CX2 is least stable, followed by silicon X2. Then you will have, can I see, Geet, germanium X2, Sen X2, followed by PbX2. Okay, so this is the stability of dihalides. This is the stability of dihalides. Why is this happening? Because we know that if as we go lower down the group, the inert pair effect is what? The inert pair effect is very high, and we have a considerable change in the oxidation state. So lower oxidation state are stable as we go down the group. Lower oxidation state are stable as we go down the group. You can see stability of dihalide increases as we go down the group. Okay. Next is regarding the character, whether it is ionic or whether it is covalent. Whether it is ionic or it is covalent. So you can write most of EX4 are covalent except SNF4 and PbF4. These are ionic in nature. These are ionic in nature. Right, next, hydrolysis of halides. Okay, hydrolysis of group 14 halides. So in hydrolysis, we will be adding water. So whenever you have to add water, the first criteria is that the halide, the halide, it should be having vacant d orbitals. So in this you can write except CCl4, all other tetrachlorides are easily hydrolyzed are easily hydrolyzed. Okay, why is this happen? Because as carbon does not have vacant d orbital, CCl4 cannot undergo hydrolysis. Cannot undergo hydrolysis. So in hydrolysis, what happens? You will have silicon. Let's take the example of silicon because silicon can get hydrolyzed. Plus H2O. So this will be a lone pair. And here in the silicon, we have some d orbitals which are vacant. So there will be attack of oxygen molecule to the silicon. And what will happen from oxygen molecule, one of the hydrogen will leave, right? So we have the formula of oxygen is something like this. So one of the chlorine will leave from here, one of the hydrogen will leave from here, and they will subtract HCl from here, and then you will get silicon. There will be chlorine, and there will be one OH, and one OH, and the others will be chlorine. So the same thing will happen 3 more times. So 3 HCl molecule will be removed, and you will be getting silicon that is completely hydrolyzed. OH and OH. Okay. This is known as silic acid. Write this down. Let me know if you're done. Done, guys?
Yes, sir, almost.
Almost. Okay.
Done, sir.
Done. Okay. Next point is that silicon and subsequent elements have tendency to, or rather ability to form higher halides. Okay, higher halides, and especially fluorides. For example, you will be forming as any element, and there will be 6 fluorine attached to it, and there will be a overall 2 negative charge on the ion. So you can form silicon F6 2 negative. Okay, and also write one more point that silicon F6 2 negative is possible, but silicon chlorine 6 2 negative is not possible. Not possible due to large size of 6 Cl negative ions, large size of Cl negative ions, and weak interaction of lone pair of Cl negative and Cl negative and silicon 4 positive. Done, guys?
Yes, sir, done.
So right next, that is the anomalous behavior of carbon. Anomalous behavior of carbon. Okay. Now, the first point is that carbon will be differing from the rest of the elements of group 14. Why? Due to smaller size. Anomalous behavior of carbon, that will be due to smaller size, high electronegativity, right? What is X? Chi here, high electronegativity, comma, high delta Hi, high ionization enthalpy, and the main reason is and unavailability of vacant d subshell, right? Since it is in second period and it has only what? S and p orbital. It has S and p orbital, and due to this, the main reason due to this, the covalency, the maximum covalency is what? Maximum covalency. Covalency is also written as covalence. Okay. What is maximum covalency or covalence? It means the maximum number of bonds carbon can form. It is equal to what? 4, right? It is equal to 4. That means it can only have 4 pair of electrons around it, not more than 4. It can have, and that is why it cannot expand its covalence. It cannot expand its covalence due to the unavailability of vacant d subshell. Unavailability of vacant d subshell. But see, whenever you will have this type of problem now, that you don't have vacant d subshells, then how carbon is working around? It is working around by forming p pi bonds and a strong pi bonds. So carbon can form strong pi bonds using its p orbitals, right? Now, the unavailability of d subshell, that means due to the small size, carbon was not able to form more than 4 bonds. But the same thing, that is the small size of carbon, it is helping carbon to form pi bonds. It is helping to form pi bonds. Okay. And why it can form strong? Using it p orbitals, it can form. So the pi bonds, by using pi bonds which are formed using p orbitals, it is known as p pi. P pi, it can form p pi bonds. It can form p pi bonds with itself and also other elements. For example, you can see it can form C triple bond C, C double bond C. It can form C triple bond N, right? It can form C double bond N, H. It can form C double bond O, right? It can form C double bond O. It can also form C double bond S. Okay, C double bond S. So all of these are example of pi bonds. Heavier elements, that means after carbon, heavier elements of group 14 don't form pi bonds due to large, wait a second, they don't form p pi multiple bonds due to ineffective overlapping of p orbitals. Next point is that we all know that carbon has the special property of catenation, right? Carbon has tendency to form long chains, has the tendency to form long chain, right? Long chain of itself. This property is known as catenation. The catenation property decreases down the group Why will it decrease? Because if I go down the group, the size increases and the electronegativity, it will decrease, and the tendency to show catenation will also decrease. And also you can see that the carbon-carbon bond is going to be very strong, right? The carbon-carbon bond is very strong, followed by silicon-silicon, followed by germanium-germanium, right? And after that, it is almost equal with SN-SN bond. Okay, almost equal with SN-SN bond. We're comparing only these because these have some covalent character, and then when we move to lead, it is completely metallic. So we won't be looking at the covalent bond in the metallic lead. So these are the properties which makes carbon different from the other groups. Now we will be looking at the allotropes of carbon. Allotropes of carbon are what? Diamond, graphite, and fullerenes. Okay, so you must be knowing, you must have heard about diamond and graphite. So we will write few points regarding diamond and graphite, and then we will write about fullerenes. Okay, Hamza is done. Right, next, allotropes of carbon. Allotropes of carbon. Okay. Allotropes means how are you going to find carbon in nature? How are you going to find carbon in nature? So you can find carbon is in the form of graphite. You can also find in the form of diamond, and then also you can find in the form of fullerenes. Okay, in the form of fullerenes. But fullerenes was discovered by, it was discovered very lately. It was discovered very lately. There is one more allotrope of carbon, that is graphene. Now, graphene you don't have in your syllabus. Okay, graphene you don't have in your syllabus. You have only graphite, fullerene, and diamond. So in this case, diamond and graphite, these are crystalline form. These are crystalline form. Okay, and the fullerene is the amorphous form. You can write here. The first point. There are three types. No? There are three allotropes. Three allotropes of carbon. Number one is diamond. Okay, now diamond is what? Diamond is crystalline. Second is graphite. Second is graphite. Graphite is also crystalline. Third is fullerenes. So we'll study about fullerenes when we talk about fullerenes. Okay. Now, first of all, diamond. Diamond. First of all, it has a crystalline structure. That means there will be crystal atoms, and each of the carbon atom are sp3 hybridized. sp3 hybridized. Now, next is, that means all the carbon atom is connected to 4 carbon atoms. Okay, so it forms a network of carbon atoms in which each carbon is attached or bonded to 4 carbon atoms. Attached or bonded to 4 carbon atoms. And this network, and then you have 4 carbon atoms attached to each carbon atom. That means you're having 4 very strong bond, and then you have again next 4 very strong bond. Okay, so the structure of diamond is something like this, that if you start from here, this first carbon atom, and then you will have, so there are, this carbon atom is attached to 1, 2, 3, and 4, right? 3 and 4. And furthermore, this carbon will be attached with further 4 more. Okay, similarly, this carbon will be attached with 4 more. This will be attached with 4 more. Okay, again, so now you can see that there is a certain kind of structure that you are making, and it is going to be very strong linked and network structure, which will be then that is why the carbon gets a very hard structure. It gets very hard structure. Okay, this will be also having, so 1, 2. This will be also having, here you have 1, 2, and 3. Okay, similarly, this will be having 1, 2. You will have one this side and on that side. Okay, so all of them, they will be having 4 carbons attached to it. 4 carbons attached to it. So it is very hard. Did somebody say something?
Sir, I was saying that will the carbon bonds be packed?
What will be?
The carbon bonds should be packed in the diamond,
Packed मतलब क्या?
like linked to each other. So at
हाँ
last
हाँ
they
हाँ.
will be packed, right?
At last they will be packed. I don't
Like
understand what do you mean.
starting from one point and they'll come back to it again.
Acha, you mean it will be complete circle?
Yeah, like kind of.
Uh kind of circle. Yeah, you can think of it like that, because it is going to be three-dimensional structure, na? So it will be like this is covering the whole region. Let me see if I can get a 3D kind of structure, now then I can show you guys. So yes, that is correct. It will be completely packed. So all the carbon atom will be having 4 bonds. Okay. Bonding in diamond. Let me see if I will have a 3D model of that. Okay, it is exactly not, I can't find anything like that. But let me show you guys. Yes, can you see this screen now?
Yes, sir.
Okay, so as you can see, what can I start? Okay, I'm starting with this carbon atom. Okay, in the top, that is in the top. Okay, fine.
Yes,
See
sir.
my cursor. See my cursor. You can see my cursor.
Yes, sir.
So I'm moving down like this. Okay, I'm moving down like this, like this, like this. Okay, then at this carbon, I changed my. I'm here right now. Okay, so I came from here and I am here now. Then I can move here, and you can again trace back to the same carbon atom. Correct? Yes or
Yes,
no?
sir.
So you have to move a bit, but all of the carbon atoms, they are all connected. Okay, so this is diamond, and this is kind of cool. I never saw this before. Thanks for asking the question then. Okay, so now here you have the graphite. Okay, now in graphite, can you see that there are each carbon atom, it is connected with how many carbon atoms? Can you see and tell me? How many?
The 4.
नहीं नहीं, देखिए देख के बताइए ना. सी
The 5.
5. अच्छा, this carbon atom, it is connected with this carbon atom, this carbon atom, this carbon. 3 only. No? 5.
Okay.
See
Yes,
closely.
yes, yes, yes.
Yeah, right?
Yes, sir.
Okay. Now what happens? This carbon bond, where my cursor is, this carbon, it has a kind of very loose bond with this carbon atom. Okay. Oh God. Wait a second. Am I audible?
Yes, sir.
I'm audible. Okay, fine. Okay.